maximizing the area of an inscribed rectangle. Okay, so we are going to work on this problem of maximizing the area of an inscribed rectangle. Now, this does require a little bit of an understanding of what an ellipse is, and I'm going to go ahead and graph that for you in Desmos to show you just what this ellipse looks like. So we have x squared over 4 plus y squared equals 1. And I want to make sure you can actually see it. Let me zoom in a ton here. Almost there. I need to change my y-axis. Is way too big here. So let's go -4 to +4. There we go. Zoom out a little bit. Okay, so you can see the ellipse here. Let me do actually -3 to 3. There we go. All right, so you can see the ellipse, and we want to put a rectangle in this ellipse that maximizes the area of the rectangle. So you can visualize some rectangles in here, but ultimately I wanted to show you this ellipse because we didn't really get to do it a couple years ago when you guys were in my class for Algebra 2. I'm going to blame this on myself as well as the pandemic because normally we would have gotten a section on some conic sections. So here's an ellipse. It's the reason that it looks like this, we call this a horizontal ellipse, is because you'll notice the denominator underneath x is 4, and the denominator underneath y squared is 1. It's not there. So that means we're going up and down 1 unit, and we're going left and right the square root of this denominator, which is 2. So that's why we're going to -2 to +2. Anyway, you don't really need to know a ton about this, but that hopefully should help you a little bit in terms of when I draw this sketch. So I have an ellipse. Okay, so an ellipse, and it's a horizontal ellipse, where this is going from +2 to -2, and we're going up to +1, down to -1, and we're drawing a rectangle in here that is going to maximize the area of the rectangle. Okay, so essentially what we're trying to do, all right, is I'm trying to write the area in terms of this rectangle first. Okay, so I'm going to write down the area is length times width. All right, and what I'm going to do to help me figure this out is I'm going to focus on a point. All right, and that point is in the first quadrant. So this point right here. So once I do that, essentially what I'm saying is that when I write my length here, all right, when I write my length is going to be, if this is x and y, my length is going to be 2 of these x's, right? If this is my length, that's going to be 2x. And my width, which is like this, is going to be 2 of those y's. Okay? So my area is going to be 4xy. Now, unfortunately, I can't really move forward with this because I have 2 variables. So what I want to do is I want to use this ellipse equation up here and solve for y. So y squared equals 1 minus x squared over 4. Taking the square root of both sides, you get y equals, right here, y equals the square root of 1 minus x squared over 4. Okay, so I'm going to replace that, and to get 4x times the square root of 1 minus x squared over 4. So this is essentially the equation that I want to find the maximum of, or maximize this equation, this area. So I'm going to plug in, let me talk about the endpoints. I'm looking at my x values. You'll notice that in terms of the x-axis, the farthest right and farthest left I'm going is -2 and +2. All right, so in terms of my domain here, because I need a positive value for x, my interval that I'm looking at is between 0 and 2. So I'm going to plug in my endpoints of 0 and my endpoints of 2 into this area formula. So I get 4 times 0, which is 0. 0 squared, 0, 0 over 4, 0, 1 minus 0 is 0. 1 minus 0 is 1. Square root of 1 is 1. But 1 times 0 is still 0. Plugging in 2 I get 8 in front. 2 squared is 4. 4 over 4 is 1. 1 minus 1 is 0. The square root of 0 is 0. But 8 times 0 is 0. So essentially my endpoints are not going to be in my maximum area. So I need to find the derivative of my area. So let's write that down. Here's 4x times the square root of 1 minus x squared over 4. Okay, so I'm going to find the derivative. This is going to be using the product property that we practice so much. The derivative of 4x is 4. So times the square root of 1 minus x squared over 4. And then plus the derivative of this square root, watch how I do it, it's going to be 1/2 times 1 minus x squared over 4 to the negative 1/2 power times the derivative of inside. The derivative of 1 is 0. So the derivative of negative 1/4 x squared is going to be negative 2/4 or negative 1/2 x to the first power. Don't forget to multiply times the other one, 4x. All right, so there's a lot going on here. Let me make it a little nicer. So that's 4 times the square root of 1 minus x squared over 4. And this is going to be plus, let's see, what's going to go in the numerator? In the numerator, I have, let's write minus because we have subtraction, or I have negative in there. So minus, I'll have this 4 way over here, and this 1/2 and 1/2, right? That's 1/2 times 1/2, which is 1/4, and 1/4 of 4 is 1. So it's just going to be, looks like negative x over the square root of 1 minus x squared over 4. Okay, make sure I got all that. I think this is going to be x squared. Let me make sure that. So the 1/2, 1/2, and the 4 becomes 1. The negative x times x is x squared, so that's good. I caught that mistake. And then we're going to go. So now what I'm going to do is, since this is equal to 0, I'm going to set up a proportion that has x squared over the square root of 1 minus x squared over 4 equals 4 times the square root of 1 minus x squared over 4 all over 1. When you cross multiply, you get x squared equals. Now watch what happens here. You have 4 times. When you multiply a square root times a square root, the square root is going to go away. So you have 1 minus x squared over 4. I'm going to distribute to get 4 minus 4 over 4 becomes 1, so minus x squared. Moving the x squared to their side, you get 2x squared equals 4, or x squared equals 2. So x is equal to plus or minus the square root of 2. Now, remember the interval here, right? Plus or minus the square root of 2. I don't want to do the negative version because my values for x are between 0 and 2. So my critical point is the square root of 2. Okay, I do have one more slide. Excellent. So I'm going to plug in the square root of 2 into my area function. So a of the square root of 2 is 4 times the square root of 2 times 1 minus the square root of 2, all that squared, over 4. So that's 4 times the square root of 2 times, let's see, square root of 2 squared is 2. 2/4 is 1/2. 1 minus 1/2 is 1/2. That's the square root of 1/2. Okay, you can put those together. So that's the square root of 2 times 1/2. Half of 2 is 1. Square root of 1 is 1. So that gives us an area of 4, which when I compare that to areas of 0, I know that that maximizes my area. So the value for x we should use is the square root of 2. Now I'm not done because I need to find the dimensions for this. I told you that my length was 2x and my width was 2y. So the length is pretty straightforward. That's just going to be 2 times the square root of 2. All right, and then for my width, it's 2 times, and remember we said y was the same as the square root of 1 minus x squared over 4. So that's 2 times the square root of 1 minus x squared over 4. That's 2 times the square root of 2 squared is 2. 2/4 is 1/2. 1 minus 1/2 is 1/2. So this is going to be my width that I have. All right. And let me make that a little nicer. The square root of 1 is 1. So that's 2 over the square root of 2, which if you wanted to rationalize the denominator, it would be 2 square roots of 2 over 2, which is just the square root of 2. So here's my length, and here is my width. Okay, and my maximum area is 4 square units. Are there any units here? Nope, it's 4 square units. Okay, so there it is. That's the whole problem for maximizing this area in this inscribed rectangle inside an ellipse. Okay, we got one more. Oh my gosh, guys, we're so close. If you've made it this far, good on you. We got one more that minimizes the surface area. Okay, so for our last one, we're going to be minimizing the surface area here. And the only thing that makes this a little bit trickier is that we're not going to have a closed bounded interval like we have for the first 5. So on this one, you'll see that we have an unbounded interval. Value just has to be x is greater than 0. And you'll see, again, we'll do the algebra with the calculus, but I'll show you on Desmos as well to kind of show you. There's a simpler way to do this without doing all the algebra. So we have a rectangular box with a square base. Okay, so rectangular box with a square base. So we have our open top and a volume of 216 cubic inches to be constructed. All right, so we have, let's see, what do I want to use for my letters here? I'm going to have X for this one, and then I'm going to have an X for this one, and then Y for my vertical one up there. So I need to find the surface area of this box. So the surface area is going to have, if I look at the vertical ones, I'm going to have X and Y as the area of those rectangles. So that's going to be 4 of them, right? There's 4 vertical faces, 1, 2, 3, 4, that are facing, we count 1, 2, 3, and then on the backside. So that's 4 times X and Y. And then plus, I just need the area of this base because we said the top is open. So the base of the area, or area of the base, is going to be X times X, which is X squared. Now, I'm not ready to take the derivative and figure out what the minimum is just yet because I have 2 unknowns. But what I can do is I can figure out a way to rewrite Y using X. And in terms of the volume, that's going to be X squared times Y, right? Because X times Y, length times width times height for the volume. So, and that's the same as 216 cubic inches. So if I solve for Y, that's going to be 216 over X squared. Okay, so I'm going to plug that in for Y and get 4X times 216 over X squared plus X squared. So my surface area formula is going to be, let's see, 4 times 216. That's going to be 8 something. 4 times 216. 864. So 864 over X, because I have 2 in the bottom, 1 on the top, plus X squared. So this is what I'm going to be using in terms of finding critical points. Now, here's the thing that's different. At this point in the problem, what we've done in the past is we have looked to see what the bounded interval is and then use those endpoints first. But because it doesn't have, like a maximum value for X that I need to worry about, I just need X to be positive. So I'm just going to find the critical points and figure out what makes that derivative equal to 0. And that'll be the critical points. And hopefully that'll be my X value for the minimum. So I'm going to find the derivative. So that's going to be, let's see, 864 times X to the negative first power. That's going to be negative 864 times X to the negative second power plus 2X. Write that a little nicer here. Negative 864 over X squared plus 2X. I need to set that equal to 0. So if I move the 864 over X squared to the other side, I get 2X over 1. We have a proportion. I get 2X cubed equals 864, or X cubed equals 864 divided by 2, which is 432. So to find X, I take the cube root of both sides. So the cube root of both sides will give me my value for X. So X is, let's see, what is the cube root of 432? Cube root of 432 is 7.5 7.56 approximately. So approximately 7.56. Okay, so this is what I should use for x to minimize our surface area. And then to find y, remember y was the same as 216 over x squared. So to find y, I'm going to do 216 over this 7.56 squared. All right, so let's see, 7.56 squared divided by 216, flip it. Where's my 1 over? It is. And you get 3.78, so approximately 3.78. So those are my dimensions that I should use. And then to minimize the surface area, when I use those, I'm going to plug in my numbers, which is 4 times 7.56 times 3.78 plus 7.56 squared. Now you'll notice when I go to Desmos, I can get the exact answer here because so far I've been doing some rounding. And as any math teacher would tell you, you want to leave your rounding to the very end. All right, so I know I wrote my work is rounded, but I'm not going to do any rounding. I'm going to type in my stuff here, which is my equation for surface area was 4xy plus x squared. 4x, no, that wasn't it. What happened when I put on the y? There it is, 864 over x, 864 over x plus x squared. And I'm looking at values between, it was 0 and I think I had 7. So I think it was like something in 3 and 5 and 7. I'll do 9 as well. So this will show you where my minimum value is, which is right there, the 7.56, which remember I found approximately 7.56. So right here is 7.56 with the surface area being minimized of 171.439. 171.439. 171.439, and this is square inches. All right, so that's it, guys. I know that was a super long video. I totally understand. A lot of this stuff, once you end up writing the equation and getting it in terms of one variable, you can just go to Desmos, type it in, find the maximum or the minimum. So that's really nice. But I did want to show you the calculus and the connection between optimization problems and the work we did with derivatives, especially with critical points. So hopefully you see the connection between those two things.